Thanks, Cameron. Okay, where did I leave you last time? Okay, so contributors and collaboration, obviously the same team. Pulled in the Geological Survey of New South Wales here because I'm writing up this long-standing thing I've been working on forever with Bob Musgrave about the Lachlan arc-terrane. Yes, well, this is why it's still delayed, but that's the next thing I promise everyone. So the talk outline, uncertainty due to the modification of Lachlan orogenesis. So really following on from my first talk. In order to understand that, you need to understand a little bit about Lachlan origin geodynamics. And I'm not going to spend much time on it, but you do need to see a few things, just so you've got your head around how crazy these systems can be with a relatively simple underlying principle. And then I'll run you through why we've got evidence, really clear, crystal clear evidence for Lachlan-timed reworking of the Stavely Arc. It's because we've got a cover group, the Grampians Group. It's all over it runs the length and breadth of the Grampians-Stavely Zone, mostly thin to absent, but locally thick. And that's copped a lot of this deformation, and that's a crystal clear timing overprint. And we've established a link between that deformation you can see in the Grampians Group and the underlying bedrock. So that's really important because bedrock's obscure, but we can correlate out using geophysics. And that's led to a couple of case studies, and the case studies are actually for significantly large parts of the zone. So I can't show you case studies for all of it, or I could, but it would take a long time. These ones will show you that we've done a due diligence when it comes to trying to understand this system in great detail to undo the effects of the late deformation, and then we can apply it to the whole of the Stavely Arc terrain. Once we've done that, we get some new shapes, and out of those new shapes, give new opportunities and correlations, and we'll talk you through a couple of those. Okay, so uncertainty. Where did I leave you last time? Oh, that's right, it was this. So it'd be great if we could turn all those, or how many of those black arrows are red arrows? That's the question we're interested in. We kind of know that, there's enough drilling already to know that there's lots of igneous rocks out there, but there's a huge spectrum of range of associations from ultramafic sort of peridotite mantle sort of stuff through Neoproterozoic rift tholiites maybe, younger rift tholiites, ophilites, some rocks that might be completely exotic related to things happening further east, and then possibly some arc rocks, and then possibly some rift rocks, and then possibly some other younger unrelated rocks. How do you unscramble this omelette and try and make sense of it all? So to do that, I'm just going to give you time for the Lachlan arc-terrane. The Lachlan arc-terrane came from more regional geophysical and geological compilations, looking at data sets, pulling them all together to try and see the bigger scale patterns. And crucial to the success of that was New South Wales finally deciding to fly detailed aeromagnetics over the Murray Basin. And when they did that, they filled a critical gap and revealed a whole bunch of stuff that we didn't know was there before. And it allowed us to take, for reference, that's Stavely, so just bear that in mind. That's the scale of the whole Stavely terrain for this bigger scale model that includes all of New South Wales and runs up into Queensland. So it allowed us to take things we'd mapped in Victoria, faults mainly, and faults we knew the age of, which is the colour coding on that diagram, and use geophysics to extend them north undercover. And when we did that, some interesting things happened. And one of them was, like, for example, the Mawson fault I spoke about in the last talk, the backstop to the accretionary wedge against the Stavely Arc. It swings through 90 degrees and heads off out to the eastern Lachlan somewhere. Pretty unusual, and it's truncated by a younger yellow fault somehow. Pretty sort of crazy relationships. And we're confident in the age of these things because we see them exposed in the Great Dividing Range in Victoria. Most of that stuff in New South Wales is either buried under the Murray-Darling system, so you can't see it, or even where it's sticking out of the ground, it's intruded by granite. So it's a bit frustrating. You get some interesting rocks, but there's just lots of granites in the way. In Victoria, we're just sort of lucky. We've just happened to jag it where we've got these faults, we can see them. So that's allowed us to do a colour coding for what we think the early Paleozoic rocks of the eastern, sort of southeastern Lachlan look like. If you took all the Murray-Darling sort of and younger cover systems off. And so in this diagram, the colours don't really matter, but the orange rocks are basically what we think of the Macquarie Arc. You'll see there's a few extra bits there, including the southern Thomson Fold Belt up the north. We think that's the Macquarie Arc. You'll see why in a minute. And the other rocks are mostly sediments, and they're colour-coded by age. So the purple ones are the Silurian group in the Stall Zone, they're Cambrian turbidites, and then they just get younger and turn into the blue ones, which are the Ordovician, we'll call the Lachlan supergroup now. And you can sort of see that stuff's very widespread. The green rocks are metamorphic rocks, so that's where the blue rocks and potentially the purple rocks have been pulled apart and have become hot and heated and melted. And that happened in the Silurian. So we've got that geometry, but how do you make sense of that geometry, right? It's pretty crazy. So when you look at Eastern Australian geology, once you do this system and you run it out across the whole of the place, the geology, the early Paleozoic geology, all the rocks are pretty similar in age, but it's all screwed up. And why that's challenging is the Macquarie Arc, most people think it's an arc, I think it was a subduction zone. All the rocks you date in the Macquarie Arc all look like part of a coherent system. But when you consider this map, what it doesn't look like is a textbook subduction accretion complex. It doesn't look like what I showed you for Stavely, for example, where just, along the Gondwana margin there's a simple continent dipping system. This is what a textbook subduction accretion system looks like. And if you think about it as an analogy, you could think of it like something else that's systematic and ordered. So you could just draw a single cross-section through it and understand the whole thing. It could be something like a warehouse that's systematic and ordered. And it's also instructive because we're going to go to one tomorrow, so take note. This is what the Lachlan Fold Belt rock warehouse looks like. It's just, we can recognise bits and pieces in it, but it's just a complete mess and it's really hard to understand. And so it's been very hard to come up with a single geological model that ties it all together. There's just literally dozens of models proposed for different bits of the belt. I think it's something like this. And why that's important is because textbook warehouses can change. And this is a combination of analogue modelling for geology, but it's also H&S training for tomorrow. Now, oh, right. What happened then? How do I get that movie to run? No. Is it? Right. Okay, so it's been sitting like this for years, this warehouse. At this point, I should probably tell you it's a Russian vodka warehouse. Right. So who knows? That might have been there for 30 years, that warehouse, looked much the same the whole time. And then in the space of literally 6 seconds, it's turned into that. Now, that's interesting because we see this sort of stuff in geology. We see persistent systems that evolve through time and look really simple, and then we come and map them and they look crazy and you think, well, what, could it ever have been simple? What's the difference between the left-hand and the right-hand diagram? The difference is the appreciation of the huge potential of a small collider that's introduced into a huge organised but only metastable system. So it's standing up against gravity and it's just waiting for an excuse to fall down. If it gets that excuse, it can really fall down. And when it happens, it's going to happen pretty quickly. And when I say pretty quickly in geology, I'm talking 5 or 6 centimetres a year, the sort of rate that slabs can move. But of course, we've got millions of years to play with. And even if we had millions of years, it would still be within the era of a shrimp date. So things can change really quickly and it can be hard to get this out of the picture. So when you think about that collapsing warehouse and you think about Australian geology and you think about the possibility of a collider, I actually gave you an outline of one in the last talk. And it was Vandyland, which is the Selwyn Block and the Western Tasmanian extension. And it's sort of wedged into the centre of central Victoria. And a lot of those wrapping things are sort of kind of wrapping around it, almost look a bit like a bow wave to it. And so I guess that got us thinking about the role this collider might have played in this sort of system. And what was fortunate about this is at the same time I was doing this work based on the geology and geophysics, Louis Moressi at Monash was doing work in geodynamics where he built a numerical model scaled at a cubic kilometre down to 800 kilometres, 3,000 kilometres high and 15,000 kilometres wide, simulating the top 800 kilometres of the Earth, including the whole Earth's lithosphere, to understand subduction systems. Now, I'm not sure how to get this running. There we go. So that brown thing was a continental collider colliding into a subduction zone. When it collides, it obviously can't sink because it's continent, it's buoyant. But the uncollided bit of the subduction zone keeps subducting, but now it can't advance, so it wraps around the collider. So they had this model for a couple of years and didn't know how to use it. And simultaneously in the same city, I had a model for how Eastern Australia might have formed, but didn't precisely know exactly what would drive it. And they're both at the same scale, operating over the same time period, from the same city, and we can use that to explain. So we got a paper in Nature of this. It was a really cool result. So what this shows is in order to understand the Lachlan, we've actually had to drive forward global understanding of how subduction accretion systems work in continental collision. It's a really good result. So when you think about the geodynamics of congested subduction zones based on what the mapping and the geophysics shows in Eastern Australia and what the modelling supports, what do you see? You see from the modelling you have collision, at the bottom left there, directly along strike from extension. So this is almost an anathema to previous thinking about how these systems behave at the same time. And they have these areas which are extending and colliding and shortening have to be separated by strike-slip faults. So it's that thing in purple. And as extension goes on, you get big rifting basins occurring behind the arc. And then once linear things can become eventually really highly curved. And why that's significant is because this is exactly what we see in Eastern Australia. We see big strike-slip faults, and we can map this. It sticks out of the ground in the Victorian Alps. And we get big basins. That's the Darling Basin. It's the same age as the activity on those strike slip faults. I mean, you've got all these crazy folds. Maybe they were straight. So we got working on the hypothesis that perhaps this was just some sort of giant superimposed fold, and perhaps this was too, giant Z-shaped thing. And we can unfold it because we know the relationship between the accretionary wedge and Stavely is Cambrian, and it's still in the same position. It has not moved far. And we also know the relationships between those rocks and Tasmania hasn't changed since the Ordovician. So because we know the age of these other structures is Silurian, we've got a foundation that's stable against which we can undo that fold. So basically it means we can take these folds and stick them back against the margin and see what happens, which we did. And it's not the first time this has been done. The New England fold belt's got the same sort of thing. Turns out they're quite common. So this is our Silurian retrodeformation for the whole of Eastern Australia, and it all operates in the same stress field, and we can apply that stress field to Stavely. So we just unpack it through time. So it's over 40 million years back against the margin. And when you do, and you can sort of see the time steps there, the numerical model's doing the same thing. So you run it forwards, you can see how the model evolves, and you can run it backwards, and you can see how simplicity emerges. And so this is really good news for exploring the Macquarie Arc, because you can correlate all the different bits of the Macquarie Arc together and chase some other bits that people haven't recognised before. When you draw a cross-section across it, it pretty much looks just like Stavely. So you've got a subduction zone to the east, and it basically looks like a textbook one. So this is how we think it evolved through time. At the end of that time, when the Macquarie Arc had become extinct and the Stavely Arc had become extinct and the boundary had jumped outboard, Stavely Arc probably still looked pretty simple. And then Tasmania collided, and it caused this crazy thing to happen. And this trench wrapped around the collider, and it towed all of Northern Australia to the south in the process. And near the end of that process, it reactivated the Moyson Fault as a dextral strike slip fault, and it's got at least 100 kilometres of displacement across it. And this is very significant. You can't see it in the seismic because it really still, at the start, it had accretionary rocks next to the arc, and at the end, it had accretionary rocks next to the arc. It just moved a lot in the interim. So we didn't pick this, but we've got new data that's starting to show it, and it enables us to do a pretty good reconstruction of it. So Stavely Arc's under there. It's strike persistent, and that's where we think that's the driver of what's happened to the Stavely Arc in the Silurian Devonian. So let's just zoom back in. Starting with the Moyson Fault. So let's zoom in on a little bit of magnetic image there. This is a snapshot of the metamorphic complex, the back of the accretionary wedge just east of the Moyson Fault. And we can see two things in this bit of the image. One is that there's a repetition of the entire metamorphic complex across the Angiep Fault. And we don't know how big it is, but it's at least 30 kilometres dextral strike slip, and we can get a fault drag at the southern end there. And even in the metamorphic complex, that purple thing, that is way too systematic to be consistent with the accretionary style deformation that was occurring in the Cambrian, and it's also the wrong geometry. Instead, it looks like a drag fold that's dextral, and it's got at least 8 kilometres amplitude of displacement across the Moyson Fault against bedrock. So we knew there was quite a bit of displacement going on there, we just didn't know how much. And so we can, obviously, we've got our potential field data, we've interpreted a fault network, we can add gravity to it, secure up our fault network. These are structures that include the Grampians group, and the gravity is particularly useful for this because the Grampians is a siliciclastic, it's quite not very dense. So where you have thick Grampians group, you tend to get relatively low gravity, and where you have juxtaposition across a fault, you can see that in the gravity. So it gives you a really good age constraint. And so this has allowed us to take off a lot of the cover and try and understand what's happening in the Cambrian rocks underneath. There's a particularly thick bit of Grampians group, and it's in this thing called the Geologcal rift, and that's that grey section in the middle where the main Grampians ranges are. That's the potential field data. So what we've got on the left is a schematic model of the Stavely Arc, colour-coded fault slices there with the stall zone in yellow to the right and the Glenelg zone in blue to the west. Now we're going to start zooming in and unpacking bits and pieces of it. So this is zooming in on the main Grampians ranges. That's what the potential field data shows, but that's what the actual outcrop shows. All you see really is the Grampians group, but that's okay because the Grampians group's got some cool things going on in it. If you look at the bedding strike in the Grampians group, it's actually got a pretty complicated structural history. It was a fold and thrust belt, and then the fold and thrust belt was folded, and then the fold and thrust belt was dismembered and extended and distributed and rotated. And the evidence for that, in particular, is some weird truncations I'll point out in a minute. But the important thing is we know the age of it, because the Grampians has got late Silurian age fossils in it, and they all predate this deformation. And then all these structures, including these folds, are intruded by 400 million year old granites, and they're all post-tectonic. So they're giving us a really good time bracket of just 10, 15 million years in which we can do this thing. There's all these weird truncations in the Grampians group where there's 90-degree strike juxtapositions, and Dave Taylor and I did this work in the 90s. We'd never really understood what was going on with these. We knew they were important, we just couldn't sort it out, but we've started to see the same thing in the underlying bedrock in the potential field data now. We can tie the two together. So that's the geology, and there's a bunch of faults where we can demonstrate this connectivity between what's happening in the Grampians, so it's definitely a sort of late Silurian, early Devonian deformation event, and what's happening in the underlying Cambrian bedrock, in that these faults have continued into the underlying Cambrian bedrock. That's what they look like in the Grampians. There's a thrust fault, for example. Pretty obvious one. Not a big one, that one, but it's well exposed. These are the sort of areas we're going to use to restore. So you can see it's fully a third of the belt. I'll go as case studies today. So case study 1, retrodeformation of the Crab Nebula. Phil's already introduced it, so it's this thing up in the northwest of the Grampians. It's largely concealed, it's got the black range over it. Quite a thin veneer of Grampians group though. You can drill through most of it. It's about 100 metres thick. So pretty interesting story going on under there. And because it's Grampians group, it's not magnetic, you can pretty much just switch on your geophysics and get rid of the Grampians group and thinking about what's happening with the bedrock. So that's the Crab Nebula again, enigmatic array of Cambrian volcanic belts, and there they all are. And what's interesting about them is the terminations. So there's these terminations. So it's unlikely to imagine that they formed that way originally. What's more likely is that they were continuously have been pulled apart somehow. And so we're interested in what that somehow was and if we could restore it. There's also drag sort of folding on the ends of these things. And we thought, well, perhaps we can use this as a guide to how to match things back together. Cool thing about these faults is, that Phil alluded to, is that these faults cut the Grampians group. So Dave Taylor and I had recognised these before. So we know the age of them. They're Devonian faults. And the Grampians group unconformably covers the upright belts. So we've got definitely 2 deformation belts there. Phil's obviously done his magic with the dip modelling. And this is really crucial because we're trying to do a 3D reconstruction here. So we don't just want to do it in plan view. We want to try and understand how this system works in 3D. So there's all these different folds and local overturning of the belts adjacent to the faults, as Phil alluded to. And if we come in and have a look at the edge of the model from the northwest, you can sort of see some of the things now captured in our model. So that's the Tyre fold, for example, folding the Tyre belt. And what's important about that is that even though at surface that belt and that fold is truncated by the Henty fault where it's expressed at the surface, and that's the red line, the Henty fault's got a dip to it, so this folded belt continues at depth underneath, and then potentially you can reconstruct it with other belts at any depth in the model. So it's quite a powerful model this way. Because of our wider Lachlan fold belt understanding, we've got, at that time, a stress field to play with. It's dextral transtension, so we want to try and understand the whole system in a dextral transtensional setting. And so there's our Crab Nebula area. So there's the aeromagnetic data with the belts on it. We apply the stress field and we just start unpacking it through time. So the dextral faults are the black ones and the sinistral faults are red ones, and they're a conjugate pair in a dextral transtensional stress field. It looks like the sinistral ones were active first, so there might have been a change from sinistral transpression to dextral transtension in there. And why this is important is because this is the end result. What have we got? We've got the Tyre belt along strike from the Glenila belt, along strike from the Black Range belt, along strike from the Black Range West Mitre belt. It's all just one belt. And that's important because the Black Range belts have got a bunch of economic deposits in it, there are prospects in it. So there's Eclipse, and obviously there's the Mine Paddock, Kringle, Woolshed. There's a series of different VMS and sort of hybrid sort of systems in there. That prospectivity is now applied to all the other belts, and some of those belts have barely been looked at for, just because no one had a reason to go there. It's a big improvement. And it's simpler. It's easy to understand. This is what we think it looked like at the time the porphyries were intruding, because this deformation is Devonian. Okay, case study 2. There we go. Oh, yep. Down the southeast of the Grampians. Same thing, we can switch the Grampians off with potential field data and have a look at what's happening in the bedrock. And we've got a bit more control here because there's a bit of exposure here. So that's the Stavely belt in there. There's a bunch of other belts. That's the Bunningal belt with the offset across the Arc fault that Phil alluded to, southern end of the Dryden belt. And then there's these anomalous, interesting belts in the middle. It's a different strike and dip. And again, we've got these belt terminations to play with. We want to try and understand how these things work. On the face of it, locally, it looks like it doesn't make much sense, but I think regionally we can make sense of it. We've got some control. So in the Dryden belt, for example, because there's these marine little volcanolithic sediment sort of packages interbedded throughout it, they've got really consistent west dipping and facing directions. And that's a thin section at the bottom there. And there's outcrops in sediments blanketing the other belts, and they're giving this pretty consistent set of facings. And you can see there's an obvious reversal there. Looks on the face of it like a fold, but there's no clear axis because it looks like it's disrupted in some way. So we went to have a look at the disruption. And when we went there, we found a 150 metre wide dextral strike slip fault melange in the Cambrian bedrock. So going, oh, this is good news, because there's this great big strike slip fault that we can now infer to explain the juxtapositions in those belts. And it's dextral because we've got the stress fabrics exposed in the creek and they're really unambiguous. And what's more important is when we look at the Grampians, there's another belt on the other end, another fault on the other end there, which also affects the Grampians, the Galton fault. One of these curvatures in the Grampians that's hard to understand, and one of these juxtapositions is occurring across that fault. It's also expressed in the Grampians. So now we're starting to get a handle on the age of that fault we've found in the Cambrian. It's one of these Devonian things because it's also occurring in the Grampians. And that folded system suggests it's clockwise rotation. So if you have a look at the belts colour-coded for green and purple there, and look at the stereo plot, there's a sort of orientation of them. It looks like they're possibly rotated around some sort of subvertically plunging kink, like that. And that's a 3D view, similar sort of thing, rotating around some sort of kink, but the kink is offset, so that's why we didn't pick it. It's hard to pick, and the actual axis is buried under the Grampians, so you have to use potential field data to see it. Zooming in on the Eric fault, there it is again. Same thing, there's an arc-terrane fold adjacent to it, and you can plot up a spread of dips and strikes, and you can see it's a subvertically plunging arc-terrane. That's what that stereo plot shows there. And the fault's quite young because it's overprinting even the late sort of Cambrian porphyries, the mineralised ones. That's the buckra and diorite there with a lineated fault plane in it related to that fault. It's also dextral. So there's a whole family of these things, and we can use them to unpack it. Same thing, same strain lifts. We have to use the same system because this is being undone at the exact same time as the crab nebula is being undone, so they all have to work together. That's what the little insect diagrams are for, to show that they all work together. So we start with the system. First thing we've got to do, incidentally we've got seismic across it, that's good news. We didn't understand this and this is why. First thing we do is identify the big faults. That's the mineral system there. Escondido fault, strike slip fault, Galton fault, another strike slip fault. Let's unpack the displacement on those. And then once you've unpacked the displacement, we can undo the mega kink. It's all starting to line up. So just unfold it through time. You can see on the right there, as we're unfolding the mega kink, we're also unpacking a lot of other deformation in the belt. And at the end, we've got a simple linear system, and this is really good news because the Stavely belt lines up with the narrow pummelet belt and the Dryden belt. And now it's a mega kink. And it's tens of kilometres scale and it's dextral, just the same as the system we used to undo the Crab Nebula. And so they've all got the same mineral prospectivity. Incidentally, the Bunnigal belt lines up with the Elliott belt and now they're fault disrupted. That's why we didn't pick it. It's all hidden underneath the Grampians. And the mega kink's plunging vertically. The power of this. Okay, so the offset bit, no one's really looked at the narrow pummelet belt. Let's have a look at the narrow pummelet belt. Now we know where it is. There it is. It's almost subcropping in places. There's one drill hole into it that's really significant, trying to hit a magnetic anomaly there, but they sort of missed it probably to drill off the flank of it. There's a serpentinite that looks like the Williamson Rose serpentinite that's in the middle of the Stavely belt. And then there's a bunch of what look like to us, like porphyries with remnants and a bunch of other possible ones as well. And really they haven't been tested and they're pretty much at the surface, and this is all in the tender area. How do these things form and how can you constrain what they've done? When you have cover sequences on old systems that are brittle and mega kinking, younger cover sequences will often be ductile instead, and to accommodate that change in deformation style, you will get scissor faults across them, and it turns out that's what we think we've got in the Grampians. So if you imagine our restored belt, the blue stuff on top is the Grampians and the pink stuff is the bedrock, and you grab it and you wrench it dextrally. At the end you end up with something that looks like this, and what you have then is folds in the Grampians group that are separated from kinks in the bedrock along scissor faults. So the bedrock is kinking and rotating, the Grampians are slopping around on top. We did not pick this. It's hard to imagine. It's hard to get your head around. But now we've got the model. We can see these things everywhere. That's the Mafficking one. They're all over the shop. We've mapped them all before. We just didn't know what we were looking at. So this particular one's really great because we've got the footwall and the hanging wall all exposed in 3D. So that's a oblique view looking northeast at the Grampians. There's all the dips and strikes Dave, Taylor and I collected years ago and didn't really fully understand. But what we've got is a folded syncline, and I've just chucked it on that little cartoon at the left there as well for reference. And what we've got is a scissor fault separating north-south trending stuff from east-west trending stuff. And you can measure this stuff and you can work out what it's doing. So if you look at the two limbs of the syncline, you look at the strike of the syncline, it's wrapping around a vertical overprinting fold. That's the plunge of the fold, the yellow dot in the middle. And the axis of the thing shows the same thing. It changes azimuth, but it doesn't change plunge. So it's a vertical fold, it's refolded it. It's a scissor fold. We can use things this to constrain what's happened in the underlying bedrock. And there's a bunch of them. Okay, so we've got a lot of constraint on this now. And we can measure it. Some bits, or this bit in particular, is a bit of Grampians Group that looks like it didn't separate from the bedrock, it actually rotated with the bedrock, and we know that because at Wallora, where the arrow's pointing, that's the one place in the Grampians, one of two places where we've found an intact baseline conformity. We wondered about that because there's no fault there. Now, we can test that because now we've got stuff that's detached and hasn't rotated and stuff that has rotated and didn't detach. And we've got the faults bounding the limb, and we've got parity current data from the Grampians. So this is not our work, this is other people's work. They compiled all this stuff. And you can see the parity currents are coming from the sort of southeast heading to the northwest. And then we've got one, they're not rotated, and then we've got one that is rotated, and look at the parity currents, they're rotated. That's an arc-line test. So the Grampians is actually rotation of parity currents, potentially mapping the rotation. So we're building a lot of different data sets. So what's that mean? Well, it means these are all obvious candidates for cross-arc transfer structures that people will pick out of potential field data working in arc-terrane. They aren't. They are the consequence of subsequent Silurian deformation. They're not related to Stavely Arc activity. Don't be misled by them. However, I should say there are arc-normal transfer structures in there. They only really pop out once you've undone all this deformation, so it just shows why it's important to do this. We can take our arc, and we can just unpack it all through time, balanced everywhere, to arrive at a new shape. And that's what the belt looks like when it's all new. Much, much simpler. That's the moistened fault when it's retrodeformed with the Silurian deformation taken out. And what's interesting is it looks like it's got a bend in it, and it looks like that was a releasing bend in the middle of the fold belt, and that's probably why we ended up with mega kinks and rifts localised along it, because when that fault belt fold moved, mostly not much happened, but where there was a releasing bend, it all fell in behind it. When you apply this model to the potential field data, it looks really different, and you can start to see some possible primary arc features beginning to emerge, like these big clusters of magmatic clustering along the belt, and they're about 70, 80 k's apart. A couple of them are overthrust in the south. Pretty much common modern arc spacing for a bunch of return flow reasons due to the subducting trench. When you think about trying to understand seismic, this has been really critical because we shot seismic across it and we ended up shooting across the reverse middle limb. The middle limb is reversed, and that's why we couldn't understand what's going on. We can take this out of the seismic section to interpret the Cambrian now because it's a tripling up of the same geology. So we've applied this to the model, and basically in the Cambrian it looks like it was a pretty simple just west dipping thrust stack. So this allows us to fill in the last bits of our cross-section and explain what's going on and remove a lot of the complexity and come up with a stress history. This is what happened in the Cambrian when it was Andean. The arc was being shortened into thrust belts. And they're aligned north-south, and that'll be the orientation for VMS systems except where it's been later rotated. Then there was a change in stress, and that change in stress resulted in intrusions into north-oriented rifts. This is the porphyry event, and we can see rifts located in different places of the belt by clusterings of Lake Cambrian magmatic rocks. And then it went back into dextral sinistral transpression for quite a long time. This is a Bonambian orogeny. And at this time, the moistened fault was reactivated and the Grampians was deposited in the footwalls of the Foreland Basin. And then it was wrenched, and it went crazy. And when that happened, we got granites intruding in a different orientation because the stress field was different. And we can see that pattern all through the Lachlan fault belt, actually, but including in here. And then there's a minor event at the end. So some conclusions. So I guess the main conclusion from all this stuff is, which of these early faulted belts of early Pozoic igneous rocks are directly related to the Stavely Arc? And the answer is all of them. So that's good news for us. And so Stavely equals a narrow pummelet belt equals a Dryden belt equals Dryden North, and we drilled the northern end of it at Stavely 16. Timbula is a backthrust to the Dryden and Dryden North belts, so we'd expect at least part of it to share the same rock packages. The Bunnigal, Elliott and Grant Deeps and Brimpan belts are all the same belt. The northern end's been completely pulled apart and rotated. And the Bunawa, Grampians West, Tyre, Glen Isle, Black Range West and Mitre Rocks are all the same belt. And two of these belts have got proven resources in them, so it's a good news story. These are some summaries. leave you to read them while I take some questions, if there's time left.
Thanks, Ross.